Morning, everyone. So over the last 2 days, we started looking at titration curves. It's basically a spin-off of how we do a titration. Usually the main goal is to determine the unknown concentration, but we saw a question yesterday. It could be a completely unknown monoprotic acid. Via a titration curve here, not only do we not have to use indicators, we can actually figure out what the Ka constant should be, and we can use that to find the unknown concentration. So just let me hint at how we do a titration curve here. I would encourage you not to memorize anything, but try to just work out the logic for yourself. It's so easy for them to switch things. Oh, I'm dropping in acid or I'm dropping in base, and suddenly the curve looks completely different. You need to be able to rationalize your way through a titration curve. Today our lesson on indicators will roughly deal with that as well. So let's say I'm going to consider a titration curve between NH3 and HCl. This time what I'm going to do here is I'm going to pretend we have HCl in the burette, and I'm going to drop it into NH3. We're basically using one chemical to actually count the particles of the other chemical. It doesn't matter, like one of these could be the unknown could be on top or bottom, doesn't really matter. But the whole thing is with the titration curve, one of the chemicals you typically would need to know the concentration. What would this titration curve look like if I plotted the pH versus, in this case here, I'm dropping acid, so volume of HCl added? So some important notes for you here. Say to yourself, well, ammonia here is a weak base. Being a weak base, even before I add in any acid, the weak base is going to be definitely higher than 7, but not sort of pushing upwards to the 12 or 13 unless there's a really, really high molarity, probably around maybe pH 10. Okay, so it's not starting all that high. Because this one here is a weak base, the weak base here has its own equilibrium. I'm going to show you the entire equation here. We're going to become NH4 plus and OH minus. Basically, we start off with all weak base, and as I slowly neutralize off some of the weak base, I'm going to hit a point where I have sort of half the NH3 left over, and I've now picked up half the conjugate. There is always going to be a buffering region if at least one of these are weak. In this case here, again, that's one of the reactions that I need to keep in mind. The other reaction that I need to be thinking of is when the weak base here actually gets reacted with HCl, the proton basically gets donated over. Right, so we end up with NH4 plus as we expected. That's how we end up forming our conjugate. Sometimes it's just NH4 plus and Cl minus written like that, or you can just say NH4Cl, and therefore we have the water here. Normally at equivalence point, the base and the acid have killed each other off. I've perfectly killed off the H plus and the OH minus. There's no excess, but depending on hydrolysis, this salt here, which is NH4Cl, it might actually hydrolyze. Now, Cl is a conjugate of a strong acid, so this one can't go backwards. But NH4 plus definitely is a weak acid itself. NH4 plus can react with water and basically reform a little bit of NH3 and along the process forming H plus. So even though we're at equivalence, this salt here had no reason to be acidic or basic. This one here ends up producing more acids at even at equivalence point. So that's what's going to happen here. We're going to have a buffering region early on, right? I'm going to convert some of the NH3 over to the NH4 plus. Smack in the middle of the buffer region is when the concentrations are equal. This is going to steadily jump downwards when it hits the equivalence point here. And what we're going to find is where we actually end up hitting equivalence point, the pH is actually less than 7 at equivalence. Right? I can ask you questions like, oh, why is there a buffer region? Well, you say, well, I have appreciable amounts of conjugate acid, conjugate base. If I ask you, oh, swap this out for a strong base, how would the volume compare? The volumes are going to be the same for equimolar solutions. And how do you explain that the pH is less than 7 at equivalence point? Well, at equivalence point here, the moles of acid and moles of base have canceled each other out. This salt here ends up performing cationic hydrolysis, the cation hydrolyzing ending up providing you H+, so therefore it's actually acidic. In today's lesson, what we're going to do, we're going to start talking about chemical indicators. Now, indicators themselves are typically going to be either an indicator is simply a weak organic acid or a weak base. And the hint there is if something is weak, it's going to be in equilibrium. It's going to be a reversible reaction. And the nice thing about this indicator here is in the conjugate acid form, in one form when it's protonated, we're going to call this H indicator. Now this is going to be a really complicated, usually organic structure, but if I have the H, it's the acidified form. This one here is going to have some color. The conjugate base form, if I go down by an H, go down by a charge, I can write that as N- instead. This one here will have different color. I'm not going to ask you why these guys here form colors or what colors they end up forming. They just need to be able to change colors. Even for, say, phenolphthalein, I'm going to, so phenolphthalein here, these are actually on your data booklet. Every indicator is its own chemical, it has its own Ka constant. It will have a relatively acidic pH. It's going to have a color 1 when it's an acid. It's going to have a color 2 when it's sort of above that transition point. Even if phenolphthalein was colorless, that's set apart from it being pink. That would still consist of it being an indicator. The whole point of a titration curve was to stop when we hit equivalence. Within a very narrow range of just dropping solution in, we go from the last hydroxide particle, we kill it off, and now we have an acid particle, an acidic pH. I want to have an indicator that roughly changes pH, roughly around where I expect the pH to be. I mentioned to you this sort of silly analogy. What if I have an indicator that changes color at pH 3? Now, for sure, the indicator changes color. For sure, that's reversible. I get to watch for the color change to occur, but that color change is happening way too late. It doesn't tell me anything about the equivalence point. That would not be a good choice of indicator. So although the equivalence point, stoichiometric point here we've been talking about here, today we're going to mainly focus on the indicator itself, and we're going to talk about choosing the right indicator that roughly has a transition point close to your equivalence so that when the color changes, I know the reaction should be stopped. So just a small little section here on indicators. Bromothymol blue is another common name for an indicator. In Hn, this is the acid form. It's yellow. In the base form, when it's lost a proton, it's blue. You can actually do this in a little more detail here. In an acidic solution, there is an excess of H+. So imagine I have an acid solution like HCl. I drop in a few drops of bromothymol blue. Right? Don't need a lot of it. Bromothymol blue itself is this sort of equilibrium here. It realizes that there are already a ton of H pluses in solution. If there's a lot of H plus, how is that going to shift the equilibrium? The H plus is going to go high. This one here is an equilibrium. I'm going to shift to the left. So the indicator is forced in its acid color form because the equilibrium ends up shifting left. In a similar way here in a basic solution, there's a deficiency of H plus. Your OH minuses have basically killed off the H plus. That's neutralized. That's ending up forming water. As it pertains to the indicator's equilibrium, by pulling down the H plus, I force the equilibrium to the right. Equilibrium shifts right. So based on that there, you can say deficiency H plus, or you can say there's an excess or an addition of OH minus. So in general, if you're in acidic solution, because the equilibrium shifts to the left, you're forcing the indicator to be in the acid form. It's the Hn form. Just like any equilibrium here, you're always going to have base form. It's just the relative proportions. If you have more of the acid type than the base type, we're overall in the acid form. So we can conclude here, there are more. The acid form for bromothymol blue is yellow. So there are more yellow than blue. So the solution appears, it just changes to a yellow. Right? It's in the acid color in an acidic solution. Now what about in a basic solution? In a basic solution, we saw that the equilibrium shifts the opposite way. It converts the Hn over to become N minus. So the Hn concentration is actually less than the N minus concentration. So the particles that otherwise would have been yellow is now in lesser quantity than the one that's blue. We can say we actually have more of the blue particle, right? More blue than yellow. So the solution appears blue. Okay, and it's not going to be a mixture of colors unless you are exactly at the transition point, unless these two are actually equal to each other. So if you want to pull out your data booklet here, you can actually take a look at table 22. You have about 7 indicators going down. What we're told on this indicator table, you're for sure given the name of it. You're given the pKa of the indicator. That's going to be important very quickly. There's a pH range. Every chemical is its own structure. It has its own pH where it changes color. And it actually tells you later on what is its relatively acidic color and what is its relatively alkali color. Right? So let's study this in a little more detail. On the table, you're going to find bromothymol blue somewhere between a range of 6.0 to 7.6. That's when it changes from going from the acid form, which is yellow, over to the blue form. I didn't even memorize that. That was actually listed for you here, yellow to blue. Okay? So that means below pH 6, is obvious. Well, below 6, it hasn't changed yet, so the solution is going to be a yellow color. No problem there. At a pH that's above 7.6, we know, well, the indicator has now switched color here. It's now blue. What's interesting here is, what about the in-between? What about 6.0 to 7.6? Realistically, over the course of this pH here, it'll gradually change color. Just for simplicity, though, I know it's still a logarithmic scale. I know it's not perfectly, if I chop this interval in 2, let's just take the average of those numbers, 6.8. Let's just simplify things, and let's just say, even though yellow just gradually converts itself over to blue, let's just say it's yellow all the way up to 6.7, 6.79. When it hits 6.8, it ends up hitting this color change point. Anything above 6.8, 6.81 is already blue. So just for simplicity, we're going to do that. Between 6.0 to 7.6, the solution gradually changes from yellow to blue, right? And again, just for simplicity, we just take the halfway point, 6.8, right? Assuming that's a linear scale, and we're just going to give this the special name. A pH of 6.8 is the transition point. Transition point is a term that's reserved for the indicator, also referred to as endpoint. At this situation, that's when the color change occurs. That's the pH when the color change happens. And what we know here, at that point, I can't have an excessive acid form, I can't have an excessive base form. At that point, the H in the yellow form has to have matched up with the N- form. Right? So if I take a look at this generic indicator equation here, so we have indicator, I can actually, well, indicator here acting as an acid, I can actually write the Ka expression. So the Ka would actually be the base form times by the hydronium divided by the Hn. And this gives us one last nice little note here. Although this relationship is always true, right? The amounts are constantly changing as they're shifting. At the transition point, if I'm at this special pH where the color changes, because these two relative amounts are actually equal to each other, at the transition point, careful, it's not this time, I'm not saying at the equivalence point. This has nothing to do with the equivalence point. But at the transition point, these two amounts are equal. It's now showing a sort of a mixture of colors here. If I have some that are yellow, some that are blue, at the transition point, again, we're simplifying things at this midway point, we're going to have an equal number of yellow and blue. Yellow and blue together end up making green. Okay. Now, they're not going to ask you any crazy colors like what does fuchsia and magenta end up changing. It should be fairly obvious. So at that point, the acid form and the base form actually cancel out. We actually end up getting N- canceling H in at the transition point and only at that point. So therefore, we get the relationship just simplifying to become Ka is equal to H3O plus at equivalence. And again, because Ka sometimes are very tiny, when you can rewrite, take negative logs of both sides, you can actually have at roughly the midpoint, the indicator ends up changing color. So therefore, the pKa is actually going to be pH at the transition point. So if you take this range, yeah, so it should change between 6 and 7.6. You take the halfway point of 6.8, and that's when the color changes to a nice green color. Okay. In our latest titration with HCl and NaOH, we use phenolphthalein as an indicator. Why does it make sense? Why is it okay? Even though phenolphthalein, it actually changes a little bit higher. So let's just have a quick look at what that titration curve would look like. What we've done here is we've dropped the base. So NaOH was in the top solution. NaOH here is a strong base. Our hydrochloric acid is a strong acid. So we would expect there's no hydrolysis afterwards. This is just HCl. As I steadily drop in base, I'm going to steadily expect the pH to increase. So I'm going to be plotting pH versus volume of base added. Again, don't memorize this. You can just read it directly from the graph here. Because this one here is strong, I would imagine starting out fairly low. As I start adding base to it, I expect the pH to steadily climb. Looking at the neutralization, NaOH reacts with HCl and ends up forming NaCl and water. At the equivalence point, at the point when the base has killed off the acid, the moles of H plus has killed off the moles of base. So in this case, it's in a 1-to-1 ratio. I have perfectly killed off NaOH HCl. I want to just double check that the salt doesn't end up hydrolyzing. Well, NaCl breaks out to become Na plus and Cl minus. Na plus is a group 1 salt, Cl minus is a conjugate of a strong acid. It has no chance of return to HCl, so that's why if they're both spectators, no hydrolysis means this one here ends up perfectly hitting equivalence at pH 7. Well, if I know that the equivalence point here should actually, equivalence pH should be 7, and yet phenolphthalein actually changes color. We know it goes from colorless at 8.3, yeah, you can cut it into maybe 9.1 or so. That's when it switches over to pink color. Phenolphthalein actually changes color a little bit too late. It changes color from 8 to about 10. So this is a systematic issue here. Phenolphthalein does change color a little bit too late. Why is it still okay? Not only because phenolphthalein is a very common indicator. Remember, we learned that for these titration curves, within a very, very narrow range of volume of base added here, we go from having that very last H plus particle to perfectly neutral to perfectly basic. Basically, if you have the volume that blows through the pH 7, you'll probably have blown through pH 8.3 to 10. So even though technically speaking, the phenolphthalein changes color a little bit too late, when it shows even that pale pink color, it's already overshot that equivalence point. But because that's within such a narrow range, you basically have a good approximation. Okay, so since the equivalence point pH changes drastically, we go through basically pH 7 is what I want to look for, and any pH like 8.3 to 10 within a very narrow range of VB. Okay, so that's why it's okay, even though phenolphthalein does change color a little bit too late, it's still a good approximation. Okay, so the sort of conclusion of this here, every chemical indicator has its own Ka value. Based on its Ka value, it's going to have a different pH at which it changes color. I'm going to want to choose an indicator that has an endpoint or transition point close to the equivalence point that I'm looking for. So if the equivalence point I'm looking for is pH 7, I don't want to choose an indicator that ends up changing color at pH 3. Okay? In that case, yeah, the color would change, but that color change doesn't tell me anything about the solution. So let me just write that important note here. How do we choose indicators? We choose an indicator with an endpoint. Right? Has nothing to do with the stoichiometry. Endpoint is referring to the transition as when the color changes, with an endpoint close to the equivalence point, close to the point that I wanted to stop at. Okay? That's pretty much all there is to indicators here. This is an important relationship. If they ask you, well, can you find the Ka of a certain indicator, just take the pH range, find that halfway point. At that point, the acid form and the base form are cancelled out, so the pKa is equal to the pH at that point. So case in point here, if we have a range 6.0 to 7.6, the halfway mark is 6.8. This is the pH at the transition point. This is also equal to the pKa. If I ask you then, what's the Ka for bromothymol blue, I would then just take anti-log negative of the 6.8, and that would end up giving you what the constant is. I still have no clue what the structure is. I have no clue why it's colored, but at least I'm able to calculate here. The Ka is 1.6 times 10 to the negative 7. If you know that relationship, the problem is fairly easy. If you don't, it's next to impossible. Okay? So that's all that we need to really know for indicators here. We're going to apply that sort of indicator to a mixture style question here. So this is the last slide here. Sometimes when we're dealing with acids and bases, sometimes you actually have multiple acids and multiple bases. So let me just hint at this here. So we have two acids in equilibrium with each other. We can actually determine which side is favored. So now I have one big equilibrium. This weak acid by itself would have already been in equilibrium. The acetic acid would have been in its own equilibrium. Now I have multiple things in equilibrium. For this equilibrium, would you be able to find for me the Kc? Remember, Kc in general means products over reactants. A Kc bigger than 1 means products favored. A Kc that's less than 1 means reactants are favored. Right? We saw a lot of these K values here be very tiny. So far up to this point, we've pretty much been saying reactants are favored. Okay? So let's just analyze this in detail here. So we know that the ammonia here is a weak base. As a base is going to receive a proton, it's going to steal a proton from, usually we would just say steal from water, but this time it actually has acetic acid to steal from. This is now a weak acid. we wouldn't bother with the titration curve in this one here. There's too many equilibria, there's too many, it's not easy to find where the equivalence point actually is. But definitely we would still have conjugate pairs. I'm going to end up getting ammonium as ammonia's conjugate pair here, sorry, weak acid. And on the other side here, acetic acid with its conjugate base as acetate. So always we have to have one acid and one base on both sides here. Because I have two separate equilibria here, I want you to break up both of the equilibria. So let's just take a look at our acetic acid here. Our acetic acid, I'm going to write out the whole equation, as a weak acid, it's going to donate its proton. Later on, it just sort of sums up, oh yeah, it just tosses it to ammonia. Well, let me just show it in reacting with water first. So passing its football over to water, maybe water later on passes it over to ammonia. So we have this equation here. The pKa value from our database, our data booklet, is a pKa of 4.76. Right. I have an acid on acetic acid side. You'll notice as the weak base has actually formed its conjugate, I have actually formed another acid on the right-hand side. Both of them are willing to toss footballs, and at the end of the day, it is going to be reversible. But I can say in general which side is going to have the stronger team. So what about the NH4 plus side? The NH4 plus, as an acid, it's going to also be able to donate a football. It's going to become NH3, and it's going to become H3O plus. This one here similarly has a pKa value. Again, from your table, pKa, I'm going to give you this constant. They actually give it to you as a pKb for your base, so pKa is 9.25, so a little bit of work to get to that. Remember, the smaller the number, the stronger the acid. So what's happening here is I actually have an acid and a base combination on the left, an acid-base combination on the right. I'm going to want to decide which one is the stronger acid. Because the acetic acid's pKa is lower, the acid that's stronger is actually CH3COH. So although hypothetically, both the acetic acid and the ammonium can toss a football, what I'm noting here is, while the pKa is lower, I actually have a stronger acid. The CH3COH is actually a stronger team. Now, normally, you would say, well, that's a stronger team. That's the side that's favored. Remember, we're using favored in a slightly different manner here. If the side is favored, it means there's more of that at equilibrium. So I pictured this as more like a volleyball game here. Yeah, it's both teams are sort of evenly matched here, but the left-hand side team is actually stronger. If they do their job better, if they pass the protons better, they're going to actually kick the equilibrium over to the right-hand side more often. So let me just write this down in words for you here. Because we've decided which is stronger, CH3COH donates, it does its job better, donates protons better than NH4 plus. So there will be more products at equilibrium. Remember, equilibrium just means this dynamic balance, the concentrations are constant in time, but we have it in such a case here where the stronger team is this side, the ball is going to land on the right-hand side of the court way more often, and therefore, just the terminology, we're going to say products are favored. So products are favored. And if we wanted to go back, well, what is Kc then? Well, products are favored, Kc has to be bigger than 1. So we can say our equilibrium constant, Kc, is bigger than 1. This time I am going to just leave it as just a generic Kc because it's not just one acid or one base I'm looking for. It's for this overall equilibrium that I'm interested in. So as a general rule, in a Bronsted-Lowry equilibrium, in a Bronsted-Lowry acid-base equilibrium, the side with the weaker acid is favored. Right? Not because they have the stronger team, they actually have the weaker team, but because the stronger team is on the other side, they're going to kick the equilibrium over to the weak side more, so at equilibrium I'm going to have more products. Right? We can just throw in a little bit with indicators here. I'm just going to do this first one with you here. Pretty much we have a couple indicators. These are 3 different indicators. What they've identified for us here is HCl is the acid, NaOH here is the base. I don't necessarily know which indicator is which, but at least they're identifying for me which is the acid color, which is the base color. So for Hn-1, the acid color is actually blue. So if I did like Hn, it's in equilibrium with H+, with H plus and N minus. So remember, in a very heavily acidic solution, there's a lot of H plus. It knocks equilibrium over to the left-hand side. In an acid equation, Hn1 is blue. The other side here is red, because I know in base it actually turns to red. In a similar fashion, Hn2, you can do the same sort of analysis here. N2 minus here. N2 minus is yellow in an acid, blue in the base form. And similarly for the last indicator, this one here looks like phenolphthalein, because in the acid form it's actually colorless. Right? Even colorless is a color. And then in minus 3, when it's lost that proton, it turns to a pink color. Now, one important note here is these are 3 totally different chemicals. These ones here all have different Ka constants. So the range at which they change pH is actually going to be different. Let me just draft it for you here. I have no idea which indicator is where, but what I'm suggesting to you here is, for my first indicator, there's a special point that we change from blue to red. For my next indicator, again, there's a special point. I don't exactly know where at this moment, but there's a special point that we change yellow to blue. And then the third indicator, like this is why they're asking you this question, is trying to figure out here where the changes are occurring. But it actually changes from being colorless to pink. This is just sort of hints at how do they make a universal indicator, a solution that actually changes color multiple times depending on what the pH is. Well, if I have many different chemicals with their own unique transition point, if I'm, let's say this is correct, I don't know if it is, let's say I'm less than this first indicator, I'm going to have a mixture between blue and yellow. So maybe I'm going to get a greenish color here. Maybe the first one has changed color. Now it's a red and yellow. Red and yellow actually make orange. And then now it's sort of maybe between here, red, yellow, and pink. I have no idea what that makes. And then red, blue, and pink. Again, I have no idea what it makes. But every indicator only needs one transition point. Some indicators are diprotic. It can even have 2 transition points. And basically, by mixing indicators, by figuring out where all these indicators actually occur, we're going to end up seeing the colors in different regions. What they want in this question here is they want to identify, can you rank these acids in order of increasing strength? Essentially, what you're going to look at is you're going to look at, well, I know the indicator 1 is blue in acid. So these ones here are acidic enough to keep this in blue. This one here is only in red. So therefore, I would conclude that acid 1 and acid 2, these 2 are stronger than acid 3. Now, all of them, the yellow indicator here, the yellow in acid form, all 3 of them are all yellow, so that's not clear to me. Then what's going to happen is, well, it should be colorless in acid, but it's pink in base. For this third indicator, it's actually pink for acid number 1. That's actually the base color. So therefore, this is not as good an acid as acid number 2. So while I had said earlier, acid 1 and 2 was better than acid 3, stronger than acid 3, acid 2 is actually stronger than acid 1. So therefore, I can say acid 2 is going to be stronger than acid 1, is stronger than acid 3. Okay? Actually, I don't think they've given you enough information for this, so let's just skip this for now. Okay? So we just had a general overview of indicators. Indicators have an acid form, an acid color, a base form. Every indicator has its own Ka value, so it has its own special transition point where it changes color. At that point, the pH at equivalence, the midpoint of the pH range, is actually going to be the pKa, and depending on whether the overall solution is acidic or basic, the indicator would respond to different colors. Okay, we want to choose an indicator that has the right endpoint that changes color roughly where the equivalence point shows up. Okay, so have another look over this here, and let me know if you have any questions. Thanks, guys.